Hey folks, Azure Cosmos DB TV. I'm your host, Mark Brown. And this week we've got with us James Codella. James, how are you?
Good, Mark. How are you doing?
I'm doing great. It is now officially July here in Seattle. And of course, well, it's not officially till July 5th when the summer starts, but we're now here in the precisely 8 weeks of summer that we get here in Seattle. So it's why we live here for the other 10 months a year, for the trudging and the rain and just the awfulness that it is. So we're excited. I'm excited, enjoying my nice weather for the next 8 weeks. How about yourself?
Nice. Well, it's officially swampy season here in New York, but despite the humidity and heat, it's actually quite beautiful. Stay inside in the AC at the peaks and go outside and have fun afterwards.
It's beautiful fall and beautiful spring, I think, for
absolutely
there, right? So yeah, you get it 2 times a year. Here we just get a 1 8-week shot of nice weather, and that's it. And then you're done. You just kind of go back inside and hang out for 10 months and then come back out in July. So anyway, we're here to talk about something that I'm very excited about. Computed properties. This is a feature that I'm really, really excited by. It's been on our roadmap for some time. And this is now GA availability, right?
Yeah, computer properties is now generally available in Azure Cosmos DB NoSQL. We're really excited about it.
I'm totally psyched. Let's get to it. You're going to talk about kind of the feature, what it is, why people care, how to get started, and then you got a demo for us. Let's just dive right into it.
Yeah, awesome. So computer properties, right? So you know how your documents in Cosmos DB have attributes or properties, as they're called, that store the data. These could be strings or arrays or numbers or date times or any sort of the supported data types. So computed properties are actually properties that have values that are derived from the properties of your documents, but they're not persisted in the items themselves, so they don't take up storage space, right? So what I can do is any sort of complex query manipulation that I want to do on a property, I can actually define a computed property for it, and then I can reference it as many times as I want in the future, just as another property, right? And this simplifies the writing process for complex queries. And not only that, is I can index these computed properties, so I can add them to my index policy and then leverage them in my queries and in a lot of scenarios, I can actually get better performance. So lower latency and lower RU costs by using computed property compared to just having that complex query logic in my query itself.
This is great. And this is why I love these things so much and why I'm so excited is its ability to provide better performance, lower cost for some operations that you may have to do everywhere. Like you've got this example here where you're basically setting something to a lower case and then indexing that versus doing that at runtime in a query, taking everything and then projecting it lowercase or doing it in a filter predicate and then doing a match or in a quality filter there. It can be very expensive to do this kind of thing. And, in the NoSQL world, we talk about things like, hey, you want to materialize aggregates or you want to materialize other things. It's kind of part of how you optimize. This just takes that kind of a step further where you can take all kinds of, computed stuff, if you will, and then materialize that into an index and use that in your query. So, I'm just repeating what you said, but I'm super excited.
Yeah, you're right. Yeah, so let's dig into some of the details here, right? So why would you want to use computed properties? Well, I think we already talked about some of the great value props, but there can actually be scenarios where you have a reduction in the RU charge for your query, right? So by adding your computed property to your index policy, especially for large queries or really large data sets, you can realize significant RU benefits depending on the scenario. And then right along those lines, you can also see a reduction in query execution time. So lower latency for your query, faster response times for your query. And then also just makes life a little bit simpler, right? you have this complex query logic, maybe that you're going to reference multiple times. Just have a one and done thing where you define it, index it, and then use it just as any other property. So it's really easy, right? Literally a three-step process, right? So when you're creating a computer property, either using the SDK or an Azure portal, you just define what computer properties looks like. It's this typical sort of JSON style payload. And then you add the property to the index policy, as part of the included paths. And then you can refer to it in queries just like any other property. Really straightforward. So here I have an example of projection or order by, but you can use it in where clauses. It's really, really powerful. So I'm going to cut over here. Actually, I have VS Code open, so I'm going to switch my screens here.
I'll put up a link to the docs if people want to just check out AKAMS/Cosmos Computer Properties, and people can get started and look at the examples there. You said you can define it in the SDK. Can you do it also via Bicep? And
you should be able to do it via the ARM template.
Okay.
Yeah, I believe you should be able to. Yeah.
Okay. I mean, if it's G, I guess, yeah, it must be. So, all right. So you're going to show us kind of how this thing works, or at least show us in an action. So what you got? You got a notebook here.
Yeah, so I have a Jupyter notebook here. I'm a Python guy, so I'm going to use the Python SDK for Azure Cosmos DB. I have a little bit of setup that we'll do first. So we'll just walk right through it. So I'll import my packages, and then I have all my Cosmos DB connection strings and details saved in an environment file. So I'm just going to go ahead and load those preliminaries. And then I have to create a client and connect that to my Cosmos DB resource. So that's what I'm doing here. And then I am creating a database. Now, I've already gone ahead and created the database and loaded the data, so we don't have to wait for that to happen. But I'll just go ahead and run this again. So I'll do my client, do the database. And then here what we're going to do is we're going to define my computer properties, my index policy, and then we're going to go ahead and create the container that I'm going to use here. And again, like I said, I already created the container, but we'll still walk through it. So I have a couple of different examples here. I'm actually creating 4 computer properties. So I'm creating one, and it's good convention to identify any sort of created properties that you have. So I'm going to affix these with the prefix of CP underscore. So here I have CP underscore overview lower. So I have a property in my data set that I'm going to use, and it contains some descriptions of movies. You may recognize it if you came and gave a demonstration at Fabric Conference in 2024, or some of the other demos for Cosmos DB and AI scenarios. So we have a data set that contains some information about movies, and the part of this movie information are things like overviews and titles and genres of movies, etc. So what I'm going to do here in computer properties is I'm going to show a couple different examples. I have the CP underscore overview lower. So what I'm going to do here is I'm going to cast the overview to lowercase. That way I can do a more precise and efficient index scan and leverage the index more efficiently for doing some string query operations. Next, I'm going to look at the length of the overview. So there may be cases where you have maybe a string or, say, an array, and you want to have queries that have where clauses or filter predicates based on the length of, say, that string. So we're going to do that here. We have a genre field, which is actually an array in our documents. So we're going to go ahead and make computer properties for the number of elements in that array. And then I have another computer property here for vectorization, right? So hopping on, the excitement for all of our AI announcements for Azure Cosmos DB and our vector search announcements. If I have multiple properties that I want to vectorize, rather than referring to those properties one by one, I can actually concatenate them using computer property, and it's much faster and much more cost effective to reference those. And we can see here that the definition for these computer properties is just defined as a NoSQL query, right? So for my lower, it's select value lower of my overview. For the overview length, it's getting the string length. For the genre count, it's getting the length of the array using the array length system function. And then for the toVectorize property, we're just getting we're using the concatenation string system function here and adding some additional details. See, I don't just have to use property values. Actually, I can add my own strings in here, right? So I'm going to add a little bit more flavor, add a little bit more detail into this property. So when I vectorize it, it has that context.
That's a cool little use case right there, folks, if you don't quite grasp what he's doing there. But one of the things with vectorizing data is what to vectorize. Like, there's a lot of garbage potentially that doesn't make sense to vectorize to use in a vector search, like maybe goods or IDs or other stuff, that foreign keys or whatever. Like, you're doing a nearest neighbor search on text. Use text that matters, because it's going to make the query work better.
Yeah.
Right.
Yeah, exactly.
So, for a little bit for folks that may be kind of new to this vector space.
Yeah. So at the Build conference in 2024, about a month or so ago, we launched a vector search preview for Cosmos DB NoSQL. So this allows you to do semantic retrieval on data that's stored in Azure Cosmos DB using vector embeddings like those that you can create with Azure OpenAI. And as Mark's saying, to do that, there's lots of ways of vectorizing your data. And you usually want to pick the most relevant properties that you want to search over, maybe to power a chatbot or any other sort of application. So computer properties is a really great way to ahead of time say, here are the properties that I think are going to be most influential in my AI application. I'm going to vectorize these properties, and you'll define it as computer property. So you can just reference it anytime you want to vectorize it or do any sort of search operation on that data.
Yeah. So you insert your data or update it, and then go and pipe that property into an embedding function or a function that generates embeddings, and then insert that in, update that, and you're done. So that's cool.
Makes it really easy.
So you got the computed properties array, and then of course your indexing policy, where you're then calling out the path to your properties.
Yeah, so the important thing to note about computer properties is they're not automatically added to the index policy if I have a star path, right? So I need to explicitly add every computer property here. So I'm just going ahead and doing that. And then I have just a creation of my container here. So I'm going to go ahead and just run that. So I've already created everything, so it's just loading the connection to the container into deep memory. Now I have the data here. It was actually a JSON file that you can go and play around with and upload yourself if you check out the GitHub repository. I'm not going to bore you with waiting for this to insert into the database. I've already gone ahead and done this. So now what we get to do is we get to experiment with querying the data. Actually, no, before I do that, maybe it'll be a good idea for me to actually jump into the Azure portal so we can see what this looks like in the portal itself. Does that sound good?
Yeah, it sounds good. While you're doing that, I'll put up a link to our docs again. So check out all the docs for our new GA feature for computer property docs. You can go there and take a look, get started with it. And then also the notebook that James is sharing now is up on GitHub, and you can go and take a look at that. And that's aka.ms/computed properties demo. It is in Python, but you know what? It's pretty much identical to our .NET SDK. So if you're not a Python user, there you can. It's easy to translate from one to the other there. So it is Python. So all right, let's take a look. We got the portal up here.
All right, so I have my portal up here. I'm in the Data Explorer, and I'm just viewing to see what my documents look like in my collection, right? So here I have every document is a movie, so I can see that has some attributes like does it belong to a particular collection? So I see that this one belongs to the Toy Story collection, and it has a bunch of genres associated with it: animation, comedy, family, and there's some other attributes here, right? So everything that we talked about, now we can see. And if I go over here and go to scale and settings, so I can see a couple of things. One, if I go to the indexing policy, I can see the the paths for my computer properties I added. So that's good validation. But then also I can see over here that there's a great new tab here for computer properties. And so I can go and I can look at what computer properties I have defined. And if I want to make changes, I can actually make changes here in the portal as well. If I want to edit something, again, it has to be valid JSON. I can go ahead and do this right from the portal. It makes it really easy to validate that I have everything set up correctly. And if I want to make changes, it's really easy to go in and do that.
So when I do a change here, I'm guessing that's going to trigger, well, not this specifically, but when I go and add the new computed property to my index, it's going to trigger an index rebuild, correct?
Right. Yeah. So it's going to go and gradually add that to the index, depending on the size of the data you have and how many terms need to be indexed. Yeah.
Got it. So of course, and that's a full index rebuild. So of course, the length of time that takes is going to depend on how much data you got in your container and how much data you're indexing in there. But like the rest of our index rebuilds, it doesn't affect anything until the index is fully rebuilt, and then you can go ahead and see that in there.
That's right.
Zero downtime.
Very efficient process.
Yeah. Okay. Well, that's cool.
All right. So let's switch back here to my VS Code. All right. Cool.
Yep.
Cool. So, okay, we've already inserted the data. We saw what it looked like. We verified that we had some good computer properties in there. Next thing I'm going to do is just write a helper function for querying the data. So you pass in a query string, which I'll write for each use case that we're going to explore. And then I'm going to print the results. I'm going to get the RU charge because I'm requesting query metrics here. So I'm going to get the RU charge, and I'm also going to get from the query metrics itself, I'm going to get the query execution time. So this tells me how much time was spent on the backend actually executing the entire query. So we're going to use these two metrics to see how well computer properties performs compared to just writing the query outright without computer properties.
Cool. Yeah.
So again, this is a relatively small data set, about 4,400 documents. So RU charges are going to be relatively small on this data set anyway, but you can imagine if you're doing this repeatedly, you'd have significant differences, and especially at scale. So let's dive right into it. So the first example we're going to do is compare with the string length system function, right? So if I wanted to filter on say movies that have a overview with at least 100 characters in it, maybe I'm looking for really long or longer overviews, I would write a query that looks like this, right? Maybe I want the ID, I want to see what the overview is, then I'll add the square clause. So let's go ahead and execute that. So we're going to let it run. Okay, cool. So now we can see the results. So I can see that Toy Story up here, I can see a couple other movies. And then down below, I can see the RU charge, 11.67 RUs. And total execution time was 2.58 milliseconds. So really fast, right? Now we're going to query it using our computed property for overview length. And so here I'm going to look at c.id, c.overview, just as before. And this time in my where clause, I'm going to use computed property. I'm going to go ahead and run that. And I see the exact same results. And I can see the RU charge is decreased, 10.44 versus, what was it before? 11.67. So I save an extra RU just on the small data set, and the execution time is under 2 milliseconds. So even faster, right? So this is pretty cool, right? And you can imagine that as you scale to very, very large data sets, so you have sort of a little bit more selectivity in what's going on. You can this savings effect can actually propagate, right? It actually sort of explodes over time.
Yeah, and what it seems like is when you use a computer property, I mean, there's always an RU cost for an operation within there. What this fundamentally is doing is amortizing that. So the RU charge is basically on the write path, not on the read on there. And that I think is going to be more efficient because you can amortize that over a longer period of time. And since throughput is always per second, the more you can amortize it, the longer the period of time, the less expensive it is because you don't need as much throughput per second to go and do these operations. So
right,
where you can save throughput, especially on queries, because those all happen at once, that's absolutely an optimization you're going to want to make. In there.
Yeah.
If it's used in, obviously you don't want to compute a property everything. It doesn't make sense.
Yeah.
right? But it's the same calculation. Like, do I save it?
It's the same.
Can I save it now or save it later? What's the right?
Exactly. And so, and this computer property is run sort of automatically, right? So you don't have to worry about if my data changes, my computer property going to change. Yes, absolutely. It stays in sync with your data as it changes. And the effects of this can actually be quite great. Like, we've had customers that we've worked with that they've reduced their RU charge by almost 2 orders of magnitude by using computer properties in scenarios just like this.
Yeah, that's awesome. And I guess, like you're saying, it gets bigger the bigger the data set, right? So the more it scales.
That's right. Yeah, the more it scales, and also depending on the selectivity of your query filter, can really have like a tremendous impact in the cost or execution savings.
Are there particular operations that, like system functions, that get a little extra boost or that are particularly pay off well? It's like you're using a lower function here.
Yes.
Or array, not an array contains length. Are there some system functions that are rather expensive on the read path?
Yeah. So some of the string system functions are particularly expensive, primarily the contains operation, right? I think we're familiar with contains and starts with, and how starts with is more efficient use of the index. But maybe there's some scenarios where you can't use starts with, right? So the terms are put on the index in lowercase. And so being able to actually just convert those to lowercase with computer property then allows you to just do a more efficient use of the index as you're executing the query. And other than that, it really depends on, like I said, like the amount of data that you have, and then the selectivity of the filters that you're using as well.
Seems like if you like functions that require a subquery where you're diving into an embedded array would pay off particularly well. Is that generally a good characterization?
Yeah. I think there's definitely something there that maybe we should explore in a future video. That come back and do a whole thing on subqueries with you.
Like you had that count of array items and genres for the movie data set. That sounds like it would particularly you would get good ROI using a computer property.
Yeah, exactly. And we'll see an example here in just a minute. Actually, I have an example of the contains that we had just talked about, right? So, like I said, this is a data set of movies. So if I want to, find movies where Buzz Lightyear's in the overview, I can go ahead and run this query, and I can see that in my data set, looks like there's 2 movies, probably Toy Story 1 and 2. And again, it's a small set; doesn't have every movie here. But I can see it charged me, almost 20 RUs and took about 5 milliseconds to complete. Whereas if I leverage our computer property, where everything's cast to lowercase, now I can run a more efficient query here against it, right? So previously 19 RUs, almost 20 RUs in 5 milliseconds. And this time we had 17.38 RUs and about half the execution time.
Wow.
So much faster. And still some cost savings, right?
Yeah. Yep.
The next example is the array length. So this is exactly what you were just talking about, right? And we've actually had a few customers recently use this and, again, realize tremendous cost savings because they're operating at very large scales. So here we'll just take a look at a traditional query using the array lengths. Maybe I want to make sure, or I want to see what movies I have that have at least 2 genres. Maybe I want a well-rounded or well-balanced movie. So we'll go run this query. And we can see it takes a little more than 16.5 RUs and has a total execution time of 2 3/4 milliseconds. Right? If I use our computer property that actually computes this for us, we'll go ahead and run that. And I can see that my RU's charge is lower and my total execution time is also lower.
That was almost half, right?
Yeah.
What was the first one?
Yep. So it's 16.59 RUs, and it's about 9 RUs here. So not just faster execution time, but in this case, it's significantly lower RU charge.
Also order of magnitude cheaper. Yeah.
Yeah. And then finally, we'll take a look at this concatenation example, right? So this is what we had talked about there are lots of scenarios where I may want to concatenate strings or different properties in my document. So in this case, imagine that I want to vectorize these to create vector embeddings for a vector search scenario. And so in this example, I'm taking a top 20. So I'm just looking for the 20 concatenations of different documents or properties in my of 20 documents. And so I'm concatenating a string that I provide, another property, another string that I provide, another property, and so forth, right? So I'm doing this like 3 times. And we're gonna go ahead and run that. And it does it pretty efficiently, actually, right? So I can see all of these strings and concatenations, and it looks great. It costs about 4 RU, so nothing crazy, and happens in under a millisecond. Let's see if we can do a little bit better now, though, using a computed property. So, the query itself is a little bit cleaner as well because I've already defined it, right? I don't need to keep writing this over and over and over again. We'll go ahead and run that. Looks good, and I can do it in under 3 RUs and almost half a millisecond. So
yeah, that's pretty nice.
Still significant savings, about 25% savings for my RU charge here. So there's lots of different use cases for computer properties. I've just sort of touched the surface here, but you can go and check out our GitHub repo, download this demo code, play around with it, and try it for yourself.
That's cool. I put up the link again here for folks. Check out James's GitHub repo with the demo you saw today, Jupyter Notebook, all in Python. Python's fun. Keep using. I've been learning Python since February, since you and I did Fabric Conference.
Yeah.
We're going to do Python. So Python, I actually quite like it. And the notebooks are really, I have to say, I really like notebooks. I didn't like them at first. They just felt weird to me as a .NET guy. But I'm warming up to them quite a bit. They are my new console app, basically, is the way I do it, right? And not only that, you can do little UX with them using that Gradle library in there as well. So better than console app, you can actually have like a little web UX in there as well. So they're very cool, folks. .NET developers, please go and take a look. Python and doing Jupyter Notebooks, cool stuff. James, this has been good. Really enjoy seeing you, and I'm really excited about computed properties. Folks, I want you to go and check it out, test them, play with them, give us feedback, tell us what you like, tell us where we can do better, I guess. But other than that, I think right.
Absolutely. Like we'd love to hear your feedback. We'd love to hear how you're using computer properties to make your workloads even more efficient and more optimal. And if you have some scenarios that you need supported, like let us know. We'd love to keep building computing properties and keep making it successful.
Yep. You can hit us on Twitter or X, I guess it's called, at Azure Cosmos DB, and just let us know how you like them and get using them. They're just right out of the box. They're going to save you throughput, consumption, and of course make your queries faster as well. So James, thank you so much for coming on. It's good seeing you again. It's great hearing about computed properties. And I guess that's it for this week's show. So thank you everyone for joining us, and we'll see you next time.
Thanks, Mark. Thanks, everyone.
Thank you.